don't want to be in the middle of nowhere. Okay. Hi, everyone. Is everything all right? Okay, let's get started. So today we are fully exiting the world of Haskell and entering the world of imperative programming languages. And the first language we're going to look at in a lot of detail is JavaScript. But don't be afraid. Today's lecture and most of them will apply in a number of different situations. We want to look at some concrete examples. And so JavaScript, you're going to be doing most of the labs in JavaScript. So it's a good language for us to take a close look at while we are here. So today's topic, I want to talk about scope. And what do I mean by scope? I mean, when we did the lambda calculus, we talked a lot about free variables and bound variables and how we went about going ahead and executing programs in the lambda calculus, right? Which the model in the lambda calculus was the substitution model, where we literally took our program and when we wanted to evaluate it, we just went ahead and did a textual change to the program text to actually get the result of doing the evaluation. And if you think about real programming languages, that's kind of a weird thing to want to do, but at least in the lambda calculus, that's enough. We don't have to do any more work. That's sufficient for what we're trying to do. The problem, though, is the substitution model is too simple for real programming languages, in particular for programming languages that have mutable state. Take this JavaScript program, for example. It defines a variable z, which is assigned to 0, increments it, and then prints it to the screen. So how exactly do we execute this program? Well, you probably know how to execute programs like this in your head, based on what you've learned in your intro JavaScript class. But if you didn't know anything about JavaScript and you had just learned the lambda calculus and you're trying to look at real programming languages in this way, you try to maybe substitute the variable. And what the heck does it mean to, add plus plus to 0? What the heck does it mean that this program seems to print out 0 in the substitution model? So the substitution model is just completely wrong in the context of JavaScript, and we need a new model to be able to explain how exactly programs get executed. So today, the model I'm going to talk to you about is what we call the environment model. If we think about the levels of abstraction in these evaluation models, at the very, very tippy top of the abstraction ladder was the substitution model, right? It was a very abstract model. It didn't say anything about intermediate data structures. It didn't say anything about concrete machine code constraints. All it was, hey, you can literally rewrite your programs and they will, you'll compute what the right thing is simply by pencil and paper, changing your program text until you are done doing execution. So we're not going to be quite that abstract. At the same time, the environment model isn't a machine model. We're not saying precisely what is happening at the level of bits in memory. If you actually wanted to learn about how that worked, we would actually have to dive into the internals of a particular JavaScript engine like V8 or SpiderMonkey, and that would actually be pretty complicated and pretty interesting, I would say, but certainly not what you would expect out of a undergrad level class on programming languages concepts. So sorry, we're not doing that lecture. We're going to do the lecture on the environment model. So how are we going to go about doing this? So once again, I'm going to split this lecture into 4 parts. Each part is going to be demarcated by a particular example that we want to do. So at the very beginning, I'm going to talk a little bit about what exactly we're introducing in this environment model. In particular, we're going to have this new concept of environments to model scope. And so I need to explain what all the terminology is, how all of this is put together. Then we'll just look at some simple examples involving first order functions, which sort of exercise the, very normal execution that, you kind of intuitively know how it works, and it just works the way you expect. Like, it's just functions and then calling functions. You could have, gone back a few decades and things would have still worked the same way. Then we will move on to the sort of major example, the example involving free variables, right? When we were doing the lambda calculus, things were nice and simple as long as there weren't any free variables involved. But when they were, you actually, had to worry about capture avoiding substitution. And, you had this concept of lambda expressions, which could somehow remember the context they were executed in, because when you did a substitution, you actually substituted things inside of the lambda expressions. So in the environment model, we're not going to have to worry about capture avoiding substitution anymore, but we are going to have to worry about what it means to, define a function inside of another function and return it in another context. And the environment model makes it clear what exactly is going on. And it's kind of the payoff for doing all of this. Sure, we can use it to understand simple first order programs, but like, it really shines for understanding what is going on in the higher order case. And in example 4, we'll like do some serious higher order work in this situation. Okay. Let's get started in that case. As always, please shout any questions you might have as we are going along. Okay, so to start off, let's talk about what we mean by a scope. So to set the stage here, we're going to have a simple program. So this program says, var y equal 1, var z equals 0, add increment z, and then print z out. So hopefully everyone here can look at this program and say to themselves, well, what I expect to happen when I run this program is I'll print out 1 because, z had 0, and then we incremented it, and now we get to 1. So let's talk about exactly how that process happens at a mechanical level when we are in the environment model. So to model the variables that we have in scope, we are introducing the concept of an environment. In other settings, it's also called an activation record. I think structure and interpretation of computer programs popularized this particular name for it. But people often call them environments. And all the environment is it's a map. It's a map from all of the variables that are defined in your scope to the actual values that are assigned to those values, to those variables. And there may be multiple environments. Intuitively, this should make sense to you because, hey, when you call functions, the set of variables that are in scope changes. So if there are multiple environments, we need some sort of environment pointer basically saying, hey, what's the current environment that I should go look in when I say read or write a variable. And this will change when I do things like function calls. And if we're talking about at the machine level, you typically literally have a register, ESP on x86 or RSP on x86-64, a register that's dedicated to pointing to the block of memory that contains all of the stuff on your stack. So, this will keep track of what environment we are in. There's another distinction that I want to make in this picture, and the terminologies here come from C++. So JavaScript doesn't really have this concept, but it's still a useful concept when we're talking about the environment environment model, and it'll be particularly useful if you ever write serious C++. So the distinction I want to make here is the distinction between 0 and the box that 0 is in. So the 0 itself, you should think of as the value. It's the thing that is stored at the variable. But of course, you can have, multiple variables pointing to the same value. On the other hand, the location that the variable is stored in, that is like the setting of Z, and it's the slot associated with what is going on in Z. So the reason why I want to make this distinction is because, for example, when we increment Z in this example, what we are doing is we're going ahead and looking at our current environment. We say, hey, I want to read out the value of Z, so let me find Z in my environment. I'm going to go ahead and read out that value, and then I'm going to rewrite the L value, the location corresponding to the variable z, to now be 1. So I didn't actually change the value per se. All I did was I computed what 0 plus 1 was, which is 1, and then I wrote it into the location for z in this situation. If that wasn't too clear, it's okay. It's not going to be too important. Like, the examples should intuitively work, but things can get pretty hairy in languages like C++, where you can actually explicitly refer to locations as opposed to values. Okay, so just to finish off the example, so after we finish writing out z to the location that we found z in, when we do a console.log, we do the same process again. We say, okay, what's the current environment? Find the environment in question, find the variable that we're looking up, its value is 1, return that to the function, and so we actually print out 1 in this situation. Okay, so we've got environments. There's a concept of a current environment. When we read variables, we look at the current environment, find the variable there. When we write variables, we also find the current environment and, well, write it at the location that is there. You might have a question, which is, what do you do if it's not in the environment? And we'll get to that very shortly. Questions so far? I am going to pause. Questions so far? Okay, well, let's keep going. So we only had one environment in that previous example. So let's go ahead and change that and actually have a non-trivial example that has multiple environments. And so to do this, we're going to look at an example where we actually have a function and we're going to call it. So this function is our good old favorite factorial function, implemented recursively. No, you shouldn't implement factorial recursively, but I wanted a recursive function because I want multiple function calls. And so we're going to just step through how exactly we evaluate this program as, using the environment variable. Oh yeah, just memorize. Yeah. Okay, so how are we going to do this? So we are going to, let's start by executing factorial 3. So in the very beginning, we started off in this global environment. Technically, factorial, the function factorial, was in the global environment, but I've elided it just for simplicity's sake. And this environment just is basically whatever is in scope at the top level of the program, which we didn't actually define any variables, so there isn't anything. When we execute factorial 3, we want to call our function. And as I mentioned earlier, calling a function is one of the operations that causes a new environment to be allocated. So we're going to just go ahead and allocate a new environment, and we need to put some things in this environment. And what we need to put in this environment are new bindings for each of the parameters to this function. So factorial takes one parameter, n. So we've got a new environment. It's got a binding for n, mapping it to 3. Intuitively, this makes sense because, hey, we need a way to actually see 3 in this case when we're working inside this function, and we don't want to add it to the global scope because that would just be weird. There's one more box in the environment here that I put here, and this is a control pointer. And the control pointer is just a way of figuring out where we should go, what we should reset the environment pointer to when we are done executing this function, right? Because once we're done executing factorial, we are going to want to return to the top level scope. And to do that, we need to change our environment pointer to point back to the global env. So the control pointer points back to the global env in this case. You can think of these as forming a singly linked stack, which we're pushing and popping environment records off of. Okay, so we've allocated this new environment, and we've put in the parameters to the environment. And we put in the control link, which, I got ahead of myself with the slides. So yeah, control link says where to put the environment pointer when you're done. And so we can start executing the inside of this function. So we have we're going to do a read from the variable n because we need to test if it's less than or equal to 1. So how did we do that? We took the environment pointer, We walked up to the environment. We said, hey, is n defined here? N is indeed defined here. And so we get the value 3. And now we can say 3 is not less than or equal to 1. And because of that, we are going to go into the else branch. And the else branch itself has another factorial call. So we've hit our recursive call, and we're not going to do anything different, right? A function call that's recursive is just like a function call that's not. So we need to allocate a new environment and allocate a new space for the parameter for that call. And this parameter has a different value than the original activation record. Okay. Hopefully this is all very familiar, because you probably would have had a very hard time in CS without this. But I do want to point out that this was sort of like a huge innovation back in the day, because originally people just had a global store of all of the variables in their program, and there's no structure like a stack. And so when people realized that actually, hey, we could have a stack and we could rebind the same textual variable multiple times to different values, that was a huge advance forward in, abstraction in programming languages. So yeah, we take this for granted today, but people had to sweat to figure out that, oh, this is the way we should go about doing things. So anyway, we're going to go ahead and do another call, and we have the last activation record from the next recursive call, and this time n is 1, and so finally we hit the 1 is less than equal to 1 case, and we are going to return 1. That causes the environment pointer to go back to the original, so we get 1 as the return for the function, multiply it by n, and return that, which pushes the environment pointer back to this one, and then finally we do one last compute, and we get back to the global environment. Okay, so this is a very, very simple example, and most of the reason why I shared it with you is because I just wanted to make sure we've got all of the terminology straight and the model with the environment records straight. So any questions here? Okay, let's do example 3. So example 3 is now a little non-trivial. We have free variables now. So if you don't remember, free variables are variables that are not bound. So we have a function f in this example, and x is not a parameter to this function. It's free. It's in fact bound by the variable in the enclosing context. So let's go ahead and try running this example and see what happens. So we start off with, in our global context, we defined a variable named x. So we're going to set x equal to 1. So we have our environment pointer. It's pointing to the environment. It's the top level environment. We're all happy. We want to go ahead and call this function f. And so when we call a function f, we need to create a new environment. This function has no parameters, so it's a very boring environment. It's empty. The control pointer still points to the top level environment. And now we are going to try to look up the value of x so that we can log it to the console. And so now I want to pose everyone who's here a question. So previously, when I looked up variables, all I needed to do was go straight to the environment specified by the environment pointer, and I was able to find the variable right there. And I didn't have to do anything. I go to the environment, there's a variable there, use it, I'm done. There's no variable x here in this example. So where should I find x? I'm actually going to wait until people post in chat. Okay, someone has suggested walk up the chain. Do we have other suggestions? Okay, so someone else is suggesting using the control variable to walk up the stack. Another person says go to the lowest outer environment. Okay. Yeah. So I've set up this diagram in a very misleading way, right? So there's this control pointer, and we're like, hey, why don't we just walk up the stack to find the variable in question? And this is not right. And to see why this is not right, let's look at a slightly more complicated version of this example. I see someone has suggested we should throw an error. Well, in JavaScript, so certainly in many programming languages, that is what would happen. But in JavaScript, we do support higher order functions, so it does an error in this case. So to see why walking up the control pointer is not right, I need to do a slightly more complicated example. So here I've kept my function f, I've kept my variable x, and I've just added a new function g, which, what does it do? Well, it defines x locally, and then it calls f. So let's step through the execution of this function. So I call g. G is a new function, so I go ahead and create an environment for it. G doesn't have any parameters, but it does define some local variables. And when I define local variables in a function, they also go into the environment corresponding to that function. So I get a record for x here. And then I call f, so I make a new environment, and I have an empty environment for f, just like before, and I have my control link pointing to, G's environment. And now if I, follow what everyone suggested I should do in the chat, I would go to my environment pointer, I would go to f's environment. F wouldn't have x, so I would walk up the control link to G's environment, and I would try to return the x there. So that's probably not good. So in fact, congratulations everyone. This is not a bug, it's a feature. We've just implemented Emacs style dynamic scoping. So one reason why we're kind of like you should be nervous about thinking that this prints 2 is what we learned in the lambda calculus is x should somehow capture the x that was in scope at this time, right? Like in the substitution model, the way we would evaluate this program is we would just substitute this x with 1 wherever it wasn't shadowed. So it's not shadowed here, so this x should be 1. And there's no mutation here. And when there's no mutation, actually the environment model and the substitution model are supposed to give the same result. You might also be nervous about concluding that this would print 2 because you actually know JavaScript and it's like not what you were expecting in this case. So no, we should not print 2. We should print 1. So how are we going to go about doing that? How are we going to arrange for 1 to be printed in this situation? And someone said, well, we want to somehow capture x in f, right? We want to somehow have the x associated with f point to the outermost x. So what we need to do is we need to introduce a new concept. So this concept is distinct from the concept of a control pointer. So the control pointer says, where should we change the environment pointer after we return from a function? That's a very good and useful feature, but it's not what we want for doing variable lookup. So what we have now in this picture is an access link. So the access pointer says, if you don't find the variable in this environment, walk the access link to find the next environment you should look for the variable in. And you can see that although the access link and the control link coincide for G, they are different for F. The control link for F points to G, but the access link points to the top level environment. And where should these access links point to? Well, sort of intuitively, and we'll make this very precise in a moment, they should point to wherever the environment was when we define the function in question, right? So both f and g are defined at the top level, and that's why they both have access links that point to the top level environment. Of course, if f was defined inside g, then its access link should point to g's environment. But that's okay because, well, if f is defined in g, then f should capture g's definition of x, not the top level one. So we would expect it to print 2 in this case. Yeah, so these are the access links. And yeah, we use the access, in summary, we use the access links to walk up the environments to find the variable in question. We have a question in chat. Could you stick the functions into your environments so you can also store a scope pointer with each function definition that you also store somehow as a pointer or something. I guess that's sort of what you're doing. That's a great idea, and let's go ahead and do it. So how do we know to wire up the axis links, right? So I just said, hey, somehow when we make the environments, we're going to like get them in the right place. And we kind of know what we want them to look like. But mechanically, like how is the computer going to know how to do that? And the way we're going to do that is, you might think about doing it statically, but that doesn't work. I don't have the example why it doesn't work. But essentially, the problem with trying to set things up statically is when we're defining our program, we sort of don't know what all the environments are, right? The environments don't come into existence until we're actually running our program. So to know what environment a function should be associated with, that's runtime information. And so we need to record this information at runtime. So the big idea, like if there is one thing you walk away from this lecture with, it's that functions are data. That is to say, functions should carry data, and one of the pieces of data they need to carry is the environment they were created in. So let's take a look and see how this works. So to make the exposition a little more clear, instead of using the named function syntax in JavaScript, we're going to actually have, we're actually going to assign these to variables. And this just makes it clear that, hey, what we want to do is we want to actually define, we actually want to have records for these inside the environment in question, just as was suggested in chat. So we start off with a few slots, X, F, and G, and we're going to go ahead and define what these are. So the slots are empty to start with. They're undefined, and we need to walk through the things to actually say what they are. So X equals 1, that's very normal. We put the number 1 into the slot, bing. Var f equals a function. So now we're not just assigning normal value to a slot. We're going to put an actual function. And what is our representation of a function going to be? It's going to be the so-called double bubble representation. That is to say, there are two pieces of data I need to represent a function. The first piece of data stored on the right is sort of obvious. I need to store the function code itself. I need the actual, function body, because that's what I'm actually going to run if I actually call the function stored in this variable. The second piece of information, though, is a pointer to the environment that the function was defined in. And we're going to use this pointer later to set up the axis links when we call the function in question. So two pieces of data, right? The code and the context. We called these two pieces of data put together a closure because we have closed over the environment that this function was defined in. We can actually still access all of the variables that were defined in that environment. And in fact, indeed, this is what exactly this example is all about. It's all about referring to the X in the enclosing environment. And sorry, I'm getting ahead of my slides again. So we've got our environment pointer that's on the left, and we've got our code pointer, which is on the right, saying how to actually execute this function. Questions so far? Okay, so we'll go ahead and do the same idea for G. So we define G, we have a closure defined for it. Once again, the environment pointer points to our current environment, just the same as F. And the code pointer points to a different function, right? Because G's implementation is different from F's implementation. It makes sense that we want them to be different. All right, so let's actually go ahead and run the function call in question. So we call G, and like before, when we call a function, we need to allocate a new environment. We'll set the control pointer to be whatever the environment pointer was before we called into this function. We'll update our environment pointer to point to the new activation record. And now the new thing is we will set up an axis pointer on this environment to point to the environment that was saved in the function that we called. And in this particular case, right, as we mentioned before, this is the same as where the control pointer goes, but we get it from the closure here. And so when we call f, now we get the correct access pointer, because remember, f was allocated in the top level environment. It saved a pointer to the top level environment. And so when I call f, I set up my access pointer to point all the way back to the top level environment. And now I can do my access to x and get the correct value, which is 1, because I don't find it in my current environment, and then I go to the environment that the closure was allocated in, and that gives me 1. This is like it. This is like the most important example in the lecture. We can go home now. Questions so far? There's a question which is the environment pointer of f and g, do they point to the same thing? They do. Yeah, so this slide is a little hard to read. It kind of looks like one of the environment pointers is pointing to the slot for g and the other one is pointing to the slot for x. They're not pointing to specific slots. They're just pointing to the entire box. So yes, they're pointing to the same thing. Any other questions? Okay. So yeah, so just to hammer it home, right? So the most important concept in this lecture is closures consist of 2 pieces of data. They consist of the environment they were defined in and the code you need to actually execute them. There are some languages that don't support closures. A very popular one is C, right? So in C, you can have a function pointer, and that represents a code pointer to some function in question, but there is no environment associated with it. And so you cannot naively close over variables in your context in C. And we can talk a little bit more about this at the end of lecture. Yeah, you use the environment pointer to set up the access link on environments you define. There's a question which is, how do we deal with the closure if the environment is destroyed when we are pointing to it, or is GC smart enough to not do that? That's a great question. So in JavaScript, you cannot think of the stack as a thing where when you return from a function, a stack frame gets destroyed. In fact, the stack frame may stick around so long as there are closures pointing to it. There's another reason why you tend not to see closures in languages that don't have garbage collection, because it's actually a lot of work to manually manage the lifetime of things you closed over. All right, so let's do our last example involving higher order functions. So here's a kind of funny looking function. So let's pause for a moment and try to figure out what it does. So we've got a function, it takes in some variable as a parameter, and then it defines a new function, which sorry, someone's calling me. Let me just, okay. So it defines a new function and it returns that function. And what does that function do? It goes ahead and increments the variable. So what exactly is this doing? Well, we've got some code. So define x to be f0, define y to be f1, and then let's try printing what happens when I call the function in question. So if you don't know what this code does, that's okay, right? We just spent a lot of time talking about the environment model. We have all the tools we need to understand what this program actually does. Let's just go ahead and do our steps to actually figure this out. So to start off, we are going to call f with the argument 0. So what does calling a function do? It allocates a new environment. It sets up variables for each of the parameters, so c points to 0. I have elided it from the example here, but f is a function in the top level context, and its axis pointer points to the top level environment. So we set up the axis pointer to also point to the top level environment in this case. And then we need to allocate a new function. So let's go ahead and allocate this new function. So what does this new function do? Well, allocating a function doesn't do anything, right? We just need to allocate a closure. And how is the closure going to work? We'll have the code pointer point to this function, and we'll have the environment pointer point to the environment that this function was defined in, which happens to be this freshly created environment where c is equal to 0. And then when we return it, we'll bind x to be this newly allocated function. So this is a great point from our earlier question, which is, hey, how can we deal with the situation if the stack frame gets deallocated when we return from the function? And the answer is it's not, because you can get to the stack by going from x to the closure and then to the environment. So it's not dead, and in JavaScript, it will not actually get garbage collected in this situation. There's a question, which is, what is SP? That's just what the current environment is, abbreviated to stack pointer in relating to how we tend to call these things in assembly. Yeah, I just didn't want to maintain the huge arrow, so there's a little fat red arrow saying where we are. Okay, so let's go ahead and run the second function call. So once again, we need to allocate a new environment. We're going to allocate a slot for our parameter. We're going to set the parameter equal to 1. And notice that we've got a lot of activation records going on, but the access link and the control link. The control link I'm showing in blue, so don't be deceived. I just didn't want to waste space on a control link slot. The control link still points to the top level environment, and so does the access link, because that's what the access link for F points to. And it's getting a little busy, so I'm just going to go ahead and put another function that's allocated here. And once again, we have a code pointer to the same code, but we have a environment pointer pointing to this new environment. So we've got these two functions, right? They have the same code, aka return pre-increment C, but their environments are different. There's an environment for the first call to F, and there's another environment for the second call to F. And we'll bind this to Y because it gets returned in this case. Okay, so finally we call X. So calling X, what does it do? Well, we go ahead and look up X, we get the closure for it, and we need to make a new environment with the access pointer set up accordingly. This access pointer will point to the saved environment for X. And now we see that, well, okay, we remembered that the value of C was 0. So we'll go ahead and increment that, and then we'll return it. So we print 1 in this situation. For clarity, I elided Y from this. So just to step through this, omit Y for a moment. We're going to look up C. That gives us this environment. Here's 1. And then we return 1, and so we print 1 in this situation. Questions so far? So to summarize, this weird looking higher order function is actually a counter. It's a counter with persistent state. Every time we call F, we allocate a new counter with its initial value set to what you passed in for C. And then every time you call the function in question, you increment the value stored in the environment, right? And return the newly incremented value. So these are just a very fancy way of writing counters. And notice we didn't have to do any object-oriented programming to do it. We did it purely with functions. So just to say that again, we can store data with activation frames. And this is a thing people do in JavaScript. Here's a essay from Mike Bostock about so he's the primary author of a visualization library called D3.js, and his one of the things that he was trying to figure out was like what a good idiom for basically reusing configurations for charts. So basically, in D3 you can define like visualizations, and sometimes those visualizations have configurable knobs. And so the question was like, how do you go about like defining these charts while letting people modify the configuration in question? And so the solution he came to in this essay was, well, just define one of these functions which returns another function and close over the configuration passed in here so that you persistently save it with this with the chart here. And then if you wanted to get the same chart but with some different configuration, you just call chart again with some different configuration object. And it just works because that's how JavaScript works. Okay, so let's sum up the environment model. So the environment model, how does it work? So when we define functions, we allocate closures. Closures are consisted of two parts, the code pointer and the environment pointer. By the way, if it seems like I'm saying this over and over again, it's because I am. And there's not very many rules. And in the next homework, which is already out on PL Class Public, but will be due in 1.5 weeks' time, you're going to have to implement these rules. So they may seem simple right now, but if you have to actually turn them into executing code, it might not be so easy. So we're going to have closures. And when we apply functions, what happens here is we allocate new environments. We set up our access link to point to the saved environment from the closure in question. Our control link points to whatever the old stack frame pointer was, and we move our stack frame pointer to point to this newly allocated environment. And finally, when we return from a function, we use the control link to figure out how to set the stack pointer from the the sub procedure call environment to our parent call according to the control link. And that's the environment model on one slide. Any more questions? Okay. So now we're going into bonus material time. I usually end early with this deck of slides. So everything is nice and simple in all the examples in this lecture because I very carefully picked things to be nice and simple. But JavaScript has a lot of historical baggage associated with it, and so things are not always so nice and simple. So just to demarcate what's going on here, so the stuff that I was talking about, that's the stuff I'm going to examine you on. But now I want to do some applications on it to help us understand weird JavaScript programs. And fortunately for you, I am not going to examine you on these weird JavaScript programs. But I do think it's very instructive to look at these situations and figure out what's going on. So let's look at this example. So I'm not even going to just only talk it over. Let's actually try coding it up. Is this okay? Let's do it this way. Okay, we'll just do it this way. Okay, so let var y equal 10. And then we're going to define a function g, which internally defines a function f, which increments y. So it doesn't seem like we've defined y yet. So, who knows? I mean, it kind of seems like it should be pointing at the y at the top level. So we go ahead and call f. And now, hey, let's define y and print out y. And that's the end of my function. And any guesses what g will print out when I run this? Anyone? Any brave soul? Okay, I have a guess for 0. So how did we get out this guess for 0? So what we said was, hey, we define y to be 0 inside G, and then we print out y. So that seems very reasonable. And indeed, we get out 0 in this situation. Okay, so my next question, what's the value of y now? I have one guess that it's 10. Any other guesses? I have another guess that it's 11. Let me explain some of the reasoning here. So why might you think it's 11? Well, 11 is something like we called G. When we called G, we define a function called f, which increments y. There's no y currently in scope, so it seems like when I call f, I should update the y at the top level. And then I define y, but that's completely unrelated to y, and then I printed it out and it was 0. Someone said 10. 10 is the correct answer. Why is the answer 10? And to answer this question, we have to know about a little JavaScript feature that they added that's called variable hoisting. Okay, so what is variable hoisting? So variable hoisting is a very strange transformation that they decided to put in the language specification. And what variable hoisting says is when I define a function, no matter where the var declaration is inside this function, I will act as if I had pre-declared it at the very top of this function. So this function is actually supposed to be, I can get rid of those slides now. Oops. So this function is actually supposed to be, oops, I'm silly. Oh, rip. Okay. Let's do it in nano. Okay, so this function is actually supposed to be var y function f so what's happened is that var that was over here made its way all the way to the top of this function. And now it seems pretty clear that f is referring to not the y in the top level, but the y inside the function g. There's a comment in question. So if function f plus y, it will print out 1, right? And yeah, let's go ahead and add some logging to this function. So what is y before and what is y after? Let's go ahead and delete this and add the rest of the code. So it doesn't print out 1. And the reason it doesn't print out 1 is because y is not 0 when you define a variable in JavaScript and you don't give it any definition. It's actually undefined. And so trying to add a number to undefined is doesn't give you any number. It just gives you not a number. And just to verify that like I didn't change the meaning of the program when I did this, let's go ahead and unhoist the variable. Yes, it gives the same thing. So yes, the declarations are not hoisted, only the fact that the variable was defined. And if you think about why this is the case for a moment, it kind of makes sense why it acts this way, because in general, the initialization of the variable could depend on other stuff that is being computed in the function. And so how the heck are you going to hoist all of that up in this situation? So variable hoisting is kind of weird, but once you sort of wrap your head around it and the rules for it, it's actually very logical. And we don't really have to change the evaluation model very much to handle variable hoisting, right? All we need to do is instead of sort of having the idea, yes, exactly. JavaScript undefined plus one is not a number. It doesn't raise an exception. Oh, JavaScript. So so as I was saying, what was I saying? So when you allocate the environment variable when you're doing a function, you basically do the parameters and you also do all of the var bindings, and you have to do an actual syntactic analysis to find all of them. And you just allocate all the slots for it all at once. And this is like simple, but it is kind of weird. Any more questions? There's a question. Does let behave similarly or differently? That's a great question. So let's go ahead and give it a try. And I will shortly explain what let is for those of you who are not as familiar. Okay, so let does something a lot more reasonable, which is that it says that y is not defined at the point where we're trying to log it. So let's explain a little bit about what let is. So var is very weird because it has this variable hoisting thing. It's been hoisted since the very, very beginning. So we basically can't change it. We're not allowed to change it because it would break lots of code. So to get around this problem, recent versions of JavaScript have introduced a new binding form. And this binding form is called let. And basically, the way to think about let is it's trying to fix all of the weird edge casey behavior that like sort of makes variable very counterintuitive to understand when you write your programs. So as what you can see here is that let does not in fact bind let does not actually get hoisted to the top, and when we try to access y inside of f, we in fact get a it is not defined error. That might be a little puzzling, but it shouldn't be. What essentially is happening here is that when we let define a variable inside of a function, we are saying that this variable is going to be defined, but for the entire span of the function where it is not defined, it's not undefined. That's what the semantics for variables, var declarations say, but it is not defined. If this is confusing, undefined is a value, right? I can have a value that points to undefined. So in the var case, I'm trying to do vim key binding. So in the var case, I have y is undefined. But in the case here, y is not defined, and that just means that it's an error to actually access this binding. This code will work if I comment this out, because now this y properly is now referring to the top level context. So that's one of the things that let bindings try to fix, is this idea of, well, the variables are secretly defined, but they're just undefined, even if you define them randomly inside the function. Yeah, that's kind of weird. Oof. Hope that answers the question. Are there other questions? Okay, I want to show people some more weird stuff. So here's a weird thing to do. There's another question about const. Does const behave like var or let? So const is also a new addition to JavaScript, and it follows the reasonable rules. So let's do this, and once again we get a not defined. So const and let basically have the same rules. It's just that const you're not allowed to modify the value afterwards. There's another question. So let overrides the existence of the outermost definition of y to have it not yet be defined. No, I wouldn't put it that way. So let's think about the activation model, right? So the activation record model says that when calling G, I have an environment. And when it was a var declaration, I had a box for y, and it's undefined. So when you do a let, you can think of it, well, I still have a slot for y, but this is like really actually not defined. Like it's like some special, it's not a value. It's like, but the slot is still there. And so when you do a lookup, you fail to find the variable when you do the lookup in this case. Does that answer the question? Oh, there's a Twitch question. Let me see. Sorry. Yes. Ha ha ha. Because of hoisting. Yes, Twitch. I'm sorry. I saw your comment very late. Okay, so I want to show some more weird stuff. So let's go back to the battle universe of var, and I want to do something very odd, which is I want to say if false, do a var. Okay, what do people think this program is going to do? So recall that previously when we did this program, we had some situation where it was undefined and then it was nan, right? Because the y was going at this variable. So does this still get hoisted? Question mark. It's okay not to know, actually. The like important thing is to know that does this get hoisted or not is the correct question to ask, because then you can go look it up and then you can use that to figure out what this program does in the situation. And so someone has intrepidly guessed yes, and the answer is yes, hoisting does happen even in this situation. So if I comment this out, just to remind you, then it actually hits the total declaration. So there's a question here, which is, does hoisting happen before or after certain optimizations? And the answer is hoisting has nothing to do with optimizations, right? Hoisting is a property of the source program. So yes, the compiler probably knows to dead code eliminate if false in the situation, but it doesn't matter because hoisting doesn't care that about how clever your compiler is, because like what if this was some like crazy condition that's hard to understand? Well, like there's no way the compiler could figure it out. So it's purely syntactic, no matter what is inside. And there's another question, which is, yes, would let get hoisted here? So we can go ahead and do this. And we see we get the 1011 behavior. That's very interesting. And this brings me to the next point, which is a very important distinction to make in JavaScript, which is that let respects all curly braces. Var does not. So let me slightly modify this program a little bit. There are a lot of console logs. Let me delete these for a moment. Okay. So this program printed out 11. Why did it print out 11? Well, for those of you who read a lot of C++ or Java, it kind of makes sense. What happened was I locally defined y inside of these curly braces, and when the curly braces ended, I exited a scope, and therefore I no longer have a y. So this is like kind of like, it's not quite a function application, but it essentially is serving the same purpose, right? Creating a new environment record and then putting 0 into it and then getting rid of it immediately when we exit the block in question. But var does not behave that way. Var busts out of all curly braces, including if statements, loops, you name it. Vars always get hoisted all the way up to the function definition in question. So they don't have normal scoping in this way. There's a question. So let gets hoisted, and it's not where it gets existed way within curly braces. Var gets hoisted within function boundaries. Yeah. That's basically right. So another way to put it is that curly braces actually introduce scopes for let, but curly braces do not introduce scopes for var, only functions do. And so this leads to this very old chestnut, which is, sort of something that I think many JavaScript programmers have run into, which is you do something like this. For var I equals 0, I is less than 10, I plus plus, and let's allocate a little array. And then we're going to just basically, oh shoot. I haven't written enough JavaScript, so I don't remember how to do this. So I think the way to do this is, how do I add a variable into a JavaScript array? Let's just find out. I think it's push. Is it push? Let's try push. And we're going to define a new function, and this function is going to console log I. And so what we would hope to happen in this situation is we get a bunch of functions which print out the values that they were saved with. But what will actually happen is they will all print out 10. And the reason for that is because this for loop does not create new scopes, right? So all of the functions you define here are pointing at the top level scope. And so by the time you're done running this loop, I is, whatever the ending state of it was. So if I change it to 2323, I'm going to go ahead and go to the top level scope, and I'm going to get 2323. And I didn't actually manage to get new variables in this case. And so a lot of old school JavaScript code does a little trick, which looks like this. They define an anonymous function that redefines a variable, and then they immediately pass that variable to the function in question. And now this works as expected because this actually created a new scope, and so the parameter now gets set to the value I was at that point in the loop, and we get the correct behavior in this case. Or I suppose you could use let. And that also does the right thing. Questions? Was var ignoring curly braces a design decision or some optimization? That's a good question. It was probably because when they were implementing the first version of JavaScript, it was easier to basically allocate space for all of the variables up front when you executed a function. So hoisting is basically a way to basically be okay, here's all the stuff I need, and I don't have to worry about because the let model is more complicated, right? You don't have this simple model of when you allocate an environment variable, you have all of the slots ready to go, and you just fill them up with undefined. You actually have to know, oh, this thing is going to be defined, so it needs to participate in lookups, but it doesn't actually have a value. So you need to make the model a little more complicated. But it's well worth it because it's a lot more understandable for programmers, I think. There is a comment saying 10 days is not a long time. And yes, I definitely agree. It is not a long time to implement a language from tip to toe. Okay, so I want to do something a little different. I hope I have Python. Do I have Python? I do have Python. I don't have Python. No. Oh shoot. Okay. Do I have Python 2? 3? Oh, I have Python 3. Woohoo. Okay. So I want to do some Python examples. So Python is a language that has a very similar model to JavaScript, and we can reproduce many of the examples here in Python. So let's just go ahead and do the one that was kind of weird. Y equals 10. So the difference in Python is that Python doesn't actually have explicit, let's define a variable things, right? So I can't actually say I want to define a y in this context. All I can do is just set y to be equal to stuff. So what the heck is this going to do? Okay, unbound local variable y referenced before assignment. So why is this happening? Well, in Python, there's no way to say that a variable is being defined or not. So Python had to come up with some other rules about essentially saying when a variable is defined or not. So the Python rules say that whenever you do a equality, that defines a variable. So all of these are essentially defining variables. And it just so happens, like if you say y equals 1 and then y equals 2, because it's already defined, you're just overriding the variable. But doing that will cause a definition of the variable. And so now we can see that this program is ill-formed because y plus equals 1 is equivalent to saying y, okay, technically not equivalent, but it's equivalent to saying y equals y plus 1. But Python has another rule. And the other rule is that although there is a y in the context, and if I, for example, just said print y, well, this won't work either. But if I got rid of this as well, if I do all of this, Python is willing to say, okay, this y is referring to the scope here. But the moment I define y at some later point in time, Python says, well, this is kind of, a very error-prone situation, and I'm just going to bug out and say, no, you're not allowed to do that. You try to reference a variable that is going to be assigned later in this function before you did it. So this is very similar to the let behavior in JavaScript, where by simply defining something with a let later in the scope, that causes it to causes us to refuse to refer to the enclosing scopes when we do things later. Okay, so let's fix this up a little. So I can't do this example as is, but I could do something like let y equal 2, and I can still try to write this example as is. And what does this print? Hey, what the heck's going on? So we printed y here and we got 0. That's expected. But then we print the top level y and we got 10. And we were coming from JavaScript. This might be a little unexpected until we realize that the definition of y here, well, this is equivalent to let y equal 2, right? Because as I said, JavaScript doesn't let you say I'm going to define a variable. So Python has no idea that you meant to refer to the y that was not in the scope here. And so Python is going to just define a new local y inside of the body of f. And fortunately, there is a way to change the behavior. You can explicitly declare that y is global, and that will cause y to not attempt to define a new variable, but instead refer to whatever y is defined to be in the global context. There's also another keyword called non-local, which says don't try to go to the local context. Instead, try to figure it out from the binding context. So what's going on here? Well, what actually happens? So I need to just print y over here. What actually happened here was this non-local y just means, hey, set y to be the enclosing environment. And then in that case, it's G. So after I run F, now y is defined to be 2. And it only went back to 0 because then I overrode it later in this function. Questions? Okay, so we're nearly out of time, so I just want to take a step back and talk about what the point of all of this was. So I do not expect you for this class to learn all of the minutiae about like all these different languages and what their scoping rules are, right? That's not the point of this class. And I don't think you need to know the minutiae of every single language. Probably you're going to have some favorite language that you're going to write in day to day, and like knowing how these things work in that language, that'll be useful just because, you're going to want to write programs and you need to know how to write them correctly. But it's not necessary to memorize it for every single language. What is important is to have the idea that there is some model, there is an explicable set of rules that defines what the behavior of scoping is in a language. And these rules are relatively short and they vary from language to language. But basically, all you need to do is you need to look at those rules, and that will tell you what you should expect when you do things in the language. So knowing that the rules exist, knowing that these are the things that you can go look up, because like if you just see this weird behavior in a vacuum, you might not even know like what do I even Google for to like learn about the situation. And so having the basis of a model lets you say, oh, I kind of know what is going on here. I don't know exactly what the rules are, but I can guess that, there's some sort of decision being made here one way or another. And that is really, really useful in like basically like if someone gives you a completely new programming language you've never seen before and something weird happens, having this model in your head can be like, oh, I know I had some expectation that was violated, but now I can update what my model is. And I can also go look at the documentation and try to figure out what exactly is going on here. Thanks, Pseudomaze. I love PL too. So that's all I wanted to talk about today. So thanks, everyone, and see you next week.